Cornell. I even still have the mug to show for it from back in the day. So it's really a great honor to be able to come back here and give a talk, albeit virtually. Hopefully I'll be able to return to Ithaca one of these days as well. But since my time leaving Cornell, I've since transferred from gorges to cornfields and have been working as a graduate student at UIUC for the last few years. So thank you all for coming. And without further ado, I think we should begin this talk on field theories of higher order topological insulators in 2 dimensions. In case anyone wants to read up further on this, I've provided an archive link for the paper this talk is based off of. All right, so to give you an overview of what I'll be talking about today, I'm going to start off by giving you some necessary background on both normal topological insulators, as well as the newly discovered higher order topological insulators. After which, I'm going to be going into more detail on one specific model of a higher order topological insulator known as the quadrupole insulator in 2 dimensions. Following which, I'll be going over a field theory description of 2 important responses of the quadrupole insulator. First, the corner charge response, and then second, the disclination charge response. Following which, I'll be giving a unified description of both responses in terms of one theory. And upon that, I'll be ending with a prediction about how we can understand a fractional quadrupole insulator response theory, which we can think of as being the fractional analog of the quadrupole insulator, the same way that a fractional quantum Hall state is the fractional analog of an integer quantum Hall state. And of course, since this is going to be a topology talk, I am bound to include this GIF of a coffee cup turning into a donut and vice versa. So after seeing this GIF, I can presume we are all experts in topology, and I can now begin. So the interest in topology and kind of condensed matter and insulators is really going to begin with normal topological insulators, which are typically characterized by having gapped bulks as well as gapless boundaries, shown here. So for example, in 1 dimension, we have a 1-dimensional insulator with 0-dimensional edge modes. In 2 dimensions, we have a 2-dimensional insulator with 1-dimensional edge modes. And in 3 dimensions, we have a 3-dimensional insulator with 2-dimensional surfaces that are gapless. These systems are typically protected by some sort of on-site symmetry, the famous examples being particle hole symmetry, time reversal symmetry, and the combination chiral symmetry. And these systems display a non-trivial bulk in the sense that the bulk of these systems cannot be trivialized without either A, breaking one of the relevant symmetries, or B, closing the bulk band gap of the system. This has all been very well understood, and since then, there's been a new discovery that these topological insulators can be generalized to so-called higher order topological insulators, as I've shown here. The most, I would say, represented feature of these systems is that they have gapped bulks and gap boundaries, but have gapless corner or hinge modes. So for example, here in 2 dimensions, we can have a 2-dimensional insulator with 1-dimensional gapped bulk, but 0-dimensional gapped corners. And in 3 dimensions, we have a 3-dimensional bulk, 2-dimensional gapped surfaces, and either 1-dimensional gapped hinges, shown in the 2nd order row, or gapped hinges, but gapless vertices, shown in the 3rd order row. These systems are normally protected by some sort of a crystal or spatial symmetry. And to give you a quick idea for why that is, we can look at this hinge insulator, the 3-dimensional 2nd order insulator, and we can imagine that if these 1-dimensional gapless modes were not actually bound to the corners, we can imagine bringing 2 of them together and annihilating them pairwise on the boundary. That has to be impossible for some reason, and so there's a spatial symmetry is necessary to protect them, or some sort of either a crystalline symmetry or magnetic crystalline symmetry tend to be the most common ones. And as with 1st order topological insulators, these systems also have a non-trivial topological bulk in the sense that their bulk cannot be closed without either breaking the spatial symmetry or closing the band gap. Yes? Question? Oh, never mind. All right, and just for future reference, I'm going to be focusing on this talk almost entirely on this 2-dimensional 2nd order insulator that has gapless corner modes. Okay. So much of the original work done on higher order topological insulators was focused around lattice models. And the quintessential example of this is the 2D quadrupole insulator or Benalcazar-Bernevig-Hughes model named after its creators. This model can be expressed as follows with this image here on the left-hand side, which shows 4 sites per unit cell, which are connected by hopping to neighboring sites, both within the unit cell and between neighboring unit cells. The hallmark features of this system are that it has 0 energy corner modes, as well as half integer corner charges shown here. And these half-integer corner charges can be pretty well understood from the limit where you take the hopping within a unit cell, these orange bonds on the picture on the left, and set them to 0. In this case, we can exactly solve for each little plaquette of hopping terms, and we find that each of these green dots leads to a charge of E over 2. And if we look, we can find that the corners, there's only 3 green dots, indicating there's an extra half integer of charge compared to the center and boundary sites. And on the rightmost image, we see that this can be shown numerically as well with very good accuracy. This model is a topological fade directed by C4 rotation symmetry in the sense that it cannot be trivialized without breaking these C4 rotations. And as a more historical note, this model is actually equivalent to what's known as the pi flux model on a square lattice, which is essentially what happens when you take a square lattice with 1 particle per site and then thread a flux of pi for each of these sites, as shown on this leftmost image, excuse me. Since the realization on lattices and in lattice systems, there's also been a number of work understanding higher order topological physics in actual experimental systems, although with the caveat, it's mostly been in metamaterials. So for example, we have acoustic systems, phononic systems, artificial electronic lattices, and to my knowledge, the only real material, these van der Waals materials. As a caveat, I will note that there has been some idea that bismuth actually may have higher order topology in its band structure, but you actually can't really observe that higher order topology because bismuth is a semi-metal under normal circumstances. So now more back to the theoretical side again. One of the main ways to understood topological insulators as well as higher order topological insulators has been through their topological invariants. The canonical examples of this for normal topological insulators are the Berry phase in 1 dimension, the Chern number in 2 dimensions, and then the Chern-Simons 3 form in 3 dimensions, which describe these 1, 2, and 3-dimensional topological insulators. There have also been some generalizations of this to higher order topological insulators, which I won't be going over too much in detail. If you want more information, you can see the cited paper by Benalcazar-Bernevig-Hughes. But suffice to say, you can do generalizations of these invariants, which are known as the Nested-Wilson loop, which describes a 2D topological insulator with corner modes, a Wannier Chern number, which describes a 3-dimensional insulator with hinge modes, and a twice nested Wilson loop, which describes a 3-dimensional insulator with corner modes. So these are very good. And I think there's some pros and cons we recognize in terms of how we understand topology using topological invariants. I would say the biggest pro is that it is straightforward and relatively direct to compute these numbers. If I hand you a band structure and some parameters, with a few dozen lines of code, I can then find out what these various quantities are and whether or not the band structure is trivial or topologically non-trivial. That being said, there are a number of things these topological invariants don't do as well. For example, it's relatively hard to match a topological invariant with some sort of actual observable physics. I think the most famous case of this was work by TKNN, which related the Chern number to the quantized Hall conductance, but generally that connection is pretty opaque. And especially in the case of higher order topological insulators, it's actually relatively hard to show that a nested Wilson loop manifestly gives you these corner charge responses. Additionally, topological invariants are really based around the single particle picture. They're based around looking at some sort of Berry curvature of the occupied single particle band. And as such, it's very hard to apply this physics to interacting systems outside of some sort of a mean field picture. So with this in mind, one way of a complementary view of viewing topological physics, which has been very successful with topological insulators, is to use an effective field theory approach. And it's been very well shown that topological insulators can be described by topological field theories, and we can use that to understand how topological insulators respond to external gauge fields or probe fields, in particular electromagnetic fields. So the canonical example of this in 1 dimension is the polarization, which in a topological field theory is described by the Goldtone-Wilczek term shown here, where P is the polarization. Now, using just this formula, we can actually look at what happens to the charge by taking a functional derivative of this topological action with respect to the chemical potential A naught, and we find that the charge density rho is equal to the derivative of P, the polarization. This is actually nothing other than the surface charge polarization theorem from classical electromagnetism. Similarly, in 2 dimensions, we have the Hall conductance, which is famously corresponds to the quantized Chern-Simons term, from which we can take a functional derivative with respect to the vector potential and find this formula for the quantized Hall conductance, which is very well documented in experiment. And finally, in 3 dimensions, we can have a topological magnetoelectric effect, where electric field and magnetic fields are coupled to one another. This corresponds to a so-called theta term, where in the topological insulators in 3D, theta is quantized as being pi by time reversal symmetry or some sort of other symmetry. Now, if we look at this term, we can also take a functional derivative of this term with respect to the chemical potential, from which we find that the charge density is going to be equal to the divergence of B. This is known as the Witten effect and indicates that a magnetic monopole will bind charge, or equivalently, a charged particle will emit magnetic fields. All right, so we obviously, effective field theory has been very useful and very fundamental in understanding topological insulators, which brings me to my big question for this talk. Do hydrotopological physics insulators also have an effective field theory description? And in particular, we're going to focus here on the 2D quadrupole insulator, which is protected by C4 symmetry. Now, there are 2 main pieces of physics I would like for the effective field theory to describe, which have been well seen in lattice models. First is the charge bound to corners, where if we look at our lattice model with open boundary conditions, we find that corners of the quadrupole insulator are going to bind charge 1/2 modulo 1. Here throughout this talk, as a note, I'll be almost entirely focusing on the fractional amount of charge bound to something like a corner, because the integer amount can only be shifted by a local addition of a single electron, and as such, not reflect any sort of well-formed topological property of the system. But the fractional part, however, cannot be screened by local perturbations, and as thus is more robust and gives you a much better understanding of the topological physics at play. In addition to the charge bound to corners, there's actually another interesting feature of the quadrupole insulator is that charge is also bound to disclination defects of the underlying C4 lattice. Now, for those who don't know, a disclination defect is basically what happens when you take a square lattice like this, and you basically replace one of these squares with a triangle as shown here. I would say the best way to understand this is that we're actually adding in a rotation symmetry flux to our lattice in the following way. If I start with a lattice vector labeled 1 and then take it all around this triangle, which is a disclination core, we find that when we get back to our starting point, our vector has now been rotated by an angle. This angle is known as the Frank angle and is equal to pi/2 for the triangle. Similarly, I can imagine putting a pentagon in the middle instead, and now to a Frank angle of -pi/2. And we can imagine doing higher order disclinations as well by combining these triangle or pentagons as we would. Now, if we look at what happens to the quadrupole insulator when we put it on a square lattice with one of these disclinations, we find that this disclination is going to bind an extra half integer of charge, here again, modulo 1. So these are going to be the 2 main features I'm trying to understand of the quadrupole insulator using an effective field theory approach. And as it turns out, these 2 features are actually very well connected to one another. And as I'm going to show later on using quantum anomalies, actually, that if I have an insulator with gap boundaries, charge bound to disclination defects indicates that the charges is also going to be bound to corners of my system as well. Similarly, if I have a system where charge is bound to corners and my insulator has rotation symmetry, I'm then going to find that charge will also be bound to disclination defects. All right, so with this in mind, can we find effective field theory description? And to skip ahead to the end of the talk, yes, we can. Honestly, if we answer this with no, it'd be a pretty boring talk. And this field theory description is going to be as follows here, which I'm going to quickly explain and give you a little intuition for the direction we're going. This first term is known as a mutual Chern-Simons term, which involves this new gauge field B, which is a background gauge field, and a normal U1 electromagnetic gauge field A. Here, fluxes of this gauge field B are going to correspond to corners of our quadrupole insulator. And this response here indicates that charge is going to be bound to corners, in agreement with what we see in the lattice. The second term is what's known as a Win-Z term and involves a coupling between the spin connection, omega, and our electromagnetic gauge field, A. This omega is going to be a geometric connection, which is going to encode curvature of our continuum theory, and equivalently, fluxes of omega are actually going to be disclinations of our lattice. So in agreement with the lattice model, we're going to show that this term is going to bind charge to disclinations. Now, an interesting thing we're going to show as well is that this B field can actually be interpreted as a second geometric connection in addition to the first geometric connection, omega. And all these responses can be nicely expressed in this formula right here, which is the functional derivative of our effective action. From which we can tell that the electromagnetic free current is determined both by the fluxes of B, which are corners, as well as the fluxes of omega, which are disclinations. All right, before I go on any further, are there any questions here before I move on?
Just to confirm, so when
Yes.
I write this, I should be thinking of B and omega as compact gauge fields with
Yes,
just like
you should. Yes,
And
very
so,
good question. Thank you.
So all the quantization of the levels have to be followed and all that. Is that right?
Yes, very good question. And yes, that is true. They should be compact gauge fields. Thank you for that. Very good question. All right, so moving on, we're going to start with our lattice model as being our basis for finding this effective action. So the minimal model for the quadrupole insulator can be expressed in terms of this 4-band model, where these gammas are going to be the normal 4x4 anti-commuting gamma matrices we're all familiar with from field theory. And importantly, if anyone is familiar with the original work of Benalcazar-Bernevig-Hughes, the model listing here actually differs by a unitary transformation from the model they use in their paper, but the underlying physics is equivalent. It's just a more useful notation for what I'll be treating. All right, and so this model is characterized by having 2 pairs of degenerate bands, as shown here. And the spectrum is going to be gapped unless M1 and M2 vanish, and M3 is either -4 or 0. At those points, we're going to find there's a gap closing. And importantly, this model is going to realize the quadrupole insulator whenever M3 is between -4 and 0. And we want to return to this limit we saw earlier when considering the corner charges. And this model corresponds to when M1 and M2 vanish and M3 is equal to -2. All right, so let's try to understand this lattice model a bit better now, and in particular, what these M1, M2, and M3 terms are listed here actually correspond to physically. So first, there's this M1 term, which is going to be interpreted as a staggered chemical potential, which breaks C4 symmetry. This term is going to favor configurations of our lattice model where the electrons are bound to these blue sites or to these sites, which are blue here, depending on the sign of M1. The second term, M2, is going to be what I'm going to call a dimerization potential, which also breaks C4 symmetry. This term is going to favor configurations when our electrons are basically bound between neighboring sites in the Y direction or in the X direction, depending on the sign of M2. Finally, M3 is what I'm going to call our quadrupole potential, which is going to preserve C4 symmetry. For certain values of M, this is going to favor configurations where the electrons are bound to these plaquettes shown here. Or alternatively, for other values, it's going to favor configurations where the electrons are bound to sites as shown here. And as we noted before, this first one is going to be the quadrupole insulator, while the second one is going to correspond to a trivial insulator, because as we can see, there's no actual coupling between adjacent sites. All right, so with this in mind, let's now consider the continuum limit of the quadrupole insulator. The first thing to know is that the phase diagram, as shown here, as we noted earlier, has 2 band crossings between trivial and topological regimes at M3 equals 0 and M3 equals -4. Now, these continuum effective field theory are really based around long distance, low energy physics. And so we want to find a place in our phase diagram where this long distance, low energy physics is really at play. That's going to be the physics closest when we're at closest to the band crossing. So we're going to choose to look very close to this M3 is equal to 0 point. We could alternatively look at the M3 is equal to -4 point as well if we wanted to, and the results would be the same there as well. But for brevity, I'm going to only focus on this M3 is equal to 0 band crossing. If we look at the spectrum around this point, we find that we can identify 2 degenerate Dirac cones here at the pi point of the Brion zone. All right, so based upon this, the continuum Lagrangian for our quadrupole insulator is going to consist of 2 two-component Dirac fermions. And we can write this in terms of one 4-component spinor as follows, where you can written these M1, M2, and M3 mass terms in terms of one mass vector M. Now, these gamma matrices are going to be our, we can call spin matrices, which are going to form a 4D representation of SU2. Here we'll be working in Euclidean space, although we could do Minkowski space if we wanted to by a Wick rotation. And secondly, we have these tau I matrices, which are isospin matrices. These are going to form a second independent 4D representation of SU2. And here we're going to see, since we're close to this band cross we mentioned earlier, the trivial regime occurs when M3 is greater than 0, and the quadrupole insulator phase occurs when M3 is less than 0. Here we're going to be interested in the regime. We're not really worried about the second band crossing we saw earlier. So we're going to assume that we're solidly in the quadrupole regime for all values of M3 less than 0. All right. So now the first question, using this continuum Lagrangian, how do we add corners to our theory? Well, in this case, we're going to find that on the continuum limit, domain walls as well as domain corners are going to correspond to fluctuations of this mass vector m. And since we're interested in topological physics, we don't really care too much about the actual magnitude of the band gap, which is going to be set by the magnitude of this mass vector m. So we're going to separate our mass vector m into two components, a scalar and a unit vector n. And we can kind of think of treating fluctuations as n only, which leads us to a nonlinear sigma model-like description of this physics. In this language, the quadrupole insulator is going to correspond to values where n is equal to 0, 0, minus 1. The trivial insulator will correspond to n equals 0, 0, plus 1. And at domain walls, this vector n is going to wind from minus 1 to plus 1 at some other point in the unit sphere. Importantly, we know that this mass vector m has to be non-vanishing at domain wall because the domain wall of the quadrupole insulator are gapped. So this n vector has to take on a non-vanishing value even at domain walls, not just in the bulk insulating phases. And we kind of understand this physics as follows. So we take this right here, we can take a quadrupole insulator on the left, a trivial insulator on the right, and this domain wall in the center. And we can imagine that the domain wall, we actually see that the physics takes on this dimerized in the y direction pattern, which corresponds to n equal to 0 plus 1, 0. So in this case, we see that n is winding from the unit sphere from the north pole to the south pole at this domain wall. Again, this is a pretty crude approximation because it's a very short length description I have shown here, but I hope it gives you some intuition for how I'm trying to treat the continuum limit of these domain walls. All right, so this in mind, we now want to find a response theory, which is going to tell us about our charge. So we're going to include a covariant derivative involving our gauge field A, and how in particular charge is bound to fluctuations of n. So we're going to take our partition function in terms of our gauge field A, as well as our fluctuating vector n. And again, these are background fluctuations, not dynamic fluctuations. And then we can write our effective action in terms of the log of our partition function. And it's actually pretty useful to think about these things as being a diagrammatic expansion since the fermions are gapped, since the scalar m is non-vanishing. We can then compute our diagrammatic expansion, and we find the leading term is going to be this first term of the effective action involving 3 powers of n, which corresponds to this one loop diagram shown here in our effective action. This is going to be a quantized topological contribution, as we'll show, and additionally non-topological, non-quantized contributions indicated by the ellipsis. However, for our purposes, it's really not going to matter too much. All right, so let's try to understand this a bit more. So the first thing we can note is that this term involving 3 powers of n actually defines the skyrmion density of this vector n. And here skyrmion can be thought of as some sort of a vortex configuration of this unit vector n. So for example, a 2 pi or a full skyrmion correspond to this configuration where the vector is pointing down the middle and then gets pointed upwards around the boundary. And we can also consider a pi or half skyrmion where the vector field is pointing down at the middle and then winds around by 2 pi on the boundary. If we then look at our effective action, we're going to find that charge is going to be bound to skyrmions, and such that this 2 pi skyrmion is going to have charge plus 1, and this half skyrmion is going to have charge plus 1/2. Importantly, this coefficient of 1/8 pi in L effective is going to be quantized. And this quantization occurs because of 1, gauge invariance, and 2, because the total skyrmion number in our entire system is a conserved integer. And this skyrmion number is actually a topological invariant, which is related to the winding of n around the unit sphere. All right, so now for the question, based on this response theory, how can we see that corners of the quadrupole insulator actually bind a half integer of charge? Well, the first thing to note is that this vector field transforms non-trivially under C4 rotations. So in order to be C4 symmetric, we have to have that under rotations, the first and second components n are odd, while the third component is even. Because of this, and the fact that we have to wind between 2 configurations at domain walls, it has to be the case that for 2 C4 symmetric domain walls, when they meet, they have to form a half skyrmion. And we can show this based on this image right here, where if we look at our topological regime, the quadrupole where all the arrows are facing down, versus our trivial regime where all the arrows are pointing up, we see that we move around here, we have to go from the upward facing arrows, to the forward facing arrows, to the downward facing arrows, to the backwards facing arrows before returning back to the trivial regime. And this, as we noted before, actually occurs in a half skyrmion. And as noted before, half skyrmions will also bind half an integer of charge. And because of this, we can then confirm that indeed corners of the quadrupole insulator will in fact bind a half integer of charge. Any questions before I go on?
Yeah, actually, I do have a question here. So
yes, please.
It looks like C4 and C4 inverse are the exact same transformation on the ends. If I at the field theory level, how do I tell that it's, when I on the corners you actually form a half skyrmion rather than no skyrmion?
Well, I would say the important thing here is that 2 C4 rotations is not trivial because we're also changing spatial index. Sorry, can you see my mouse on the screen?
Yeah.
Yeah, so look, we're changing the spatial index as well. So we're mapping a vector field at one point to a vector field at a different point. So for example, we're mapping, say, this arrow, which would maybe be 0, 1, 0, gets mapped onto this point, which is 0, minus 1, 0. So and because of that, we have to find if we wind in one direction going around the sphere, we have to wind in the opposite direction when we come back. And that necessitates the existence of a half skyrmion.
I see.
And I can, if we have an extra time at the end, I have some more detailed slides going over this in a bit more detail, which maybe we can reach towards the end, going over the math a little bit more in detail.
Okay, thank you.
Any other questions? All right, yeah, so moving on. Now we understand some of the corner physics. And I guess, in case you're wondering that I showed you at the beginning, I showed you a different theory to describe the corner charges. I will be returning to the corner charge response later on and discussing how we can interpret it in terms of a mutual Chern-Simons description later on. But I'm actually first going to move on to disclination defects and how they bind charge. So I think the first question I would ask is, how do lattice disclinations enter the continuum theory? I think there's actually not an obvious question because lattices are a very short range description and continuum theories are very long distance description. So it's not obvious that there's a good way of implementing disclinations, lattice defects, in a continuum theory. But nevertheless, we'll persevere and find a way to do it. So on one side, we have our lattice. And when we take the continuum limit of our lattice, we end up with a manifold. Now, the important objects for our lattice are going to be the primitive lattice vectors shown here, basically point to neighboring sites in some sort of configuration. We expect that when we take the continuum limit then that these primitive lattice vectors will map onto some sort of a vector bundle over our manifold. And it turns out that that's a very natural vector bundle we can choose to identify with these primitive lattice vectors. It's what's known as the frame fields, which are sometimes called Weyl beams or tetrads, depending on the author. Here, these frame fields are related to our metric, G mu nu of the manifold, via this expression here, and are sometimes as such called the inverse metric, the square root of the metric, because you have to square them to get to the metric as shown in this equation. For our purposes, I think a good way of understanding them is to treat these mu and nu indices as some sort of large scale index and A and B as some sort of a local index. As such, we can imagine that E0 mu, E1 mu, and E2 mu form some sort of a local basis for this manifold, hence, or alternatively, a local frame, i.e. a frame field. So with this in mind, we're going to want to find a way to identify our primitive lattice vectors with our frame fields. So let's try doing this first in the context of just a perfect lattice. So no defects, normal square lattice, nothing special going on. We want to identify this A0 mu with a time direction, which is normally part of our lattice. And we want to identify then E1 mu and E2 mu with the x hat and y hat directions of our lattice. So one way we can do this is by doing this as follows, where we're setting that E0 mu is equal to 1, 0, 0, E1 mu is equal to 0, 1, 0, and Et mu is equal to 0, 0, 1, which corresponds to this choice of primitive lattice vectors. However, this choice is actually not unique. I could also equally well have chosen this, which corresponds to this choice of primitive lattice vector, which is rotated by 90 degrees. Alternatively, I could have chosen this choice or this choice, which are rotated again by 90 degrees for each other. Importantly, there's no one right choice because there's no one way to pick a x hat or y hat direction on a lattice. I am doing that when you pick an x hat or y hat direction on your lattice, you're doing it entirely by chance, an arbitrary choice. And as such, all these choices from the manifold perspective are locally indistinguishable. In a more physical language, the way of saying this is that there's actually a C4 gauge ambiguity in defining our frame field. We can either define them as being locally into either one of these configurations locally, provided we have an appropriate function to map them from one point onto another one, some sort of appropriate connection, which I'll be going into in a second. So now we set the stage for the perfect lattice. We can now consider a lattice with disclinations. And here, it's useful to think about this disclination as being a point. And if we take this primitive lattice vectors around the point, they're going to rotate by the Frank angle theta f upon encircling it. Now, because this, when we go around the disclination, we rotate our lattice vectors, we can't have a global definition of them or our frame field. And so we're going to have to use instead a coordinate patch or some sort of a local definition, for example, this red region right here. And in general, we can kind of choose to pick our frame field as being this form right here, where theta is some sort of arbitrary spatially dependent angle. Now, here we encircle the disclination, we should find that the winding of theta should be equal to our Frank angle, theta f, which corresponds to a rotation of our frame field by the Frank angle. And here, the gauge ambiguity I mentioned before corresponds to a shift of theta by some function phi, which takes values in 0, pi over 2, pi, or 3 pi over 2. So having these frame fields in hand, let's now open up a general relativity book or some sort of a different geometry book and try to learn more about the underlying manifold itself. The first thing is that, sorry, can you guys still hear me? Can I get a thumbs up?
Yeah. Yes.
Hi, can you hear me now?
Yes.
Sorry, give me a quick second. My headphones decided this was a good time for them to die on me, so I have to switch over from them to my laptop. Can you hear me now?
Yes.
All right, good. Thank you. Sorry about that, technical difficulties. All right, so now we can look at what our metric says. And first thing we note is that our metric is going to be locally flat. So our metric is going to be phi arrow, which is basically just the statement that if we look far away from our disclination, we're going to see that the normal lattice is restored. Second, we can look at the spin connection, which we can derive in the continuum from these things. Here's only going to be one non-vanishing component of the spin connection shown here. And for our definition on the middle here, it's just equal to the derivative of theta. And importantly, if we now look at how the spin connection transforms under this C4 gauge transformation, we find it transformed like a gauge field. And because of this, we can identify omega as being the gauge field for C4 rotations. We can also look at curvature, which is going to be the field strength tensor of omega in this case. And because of this, we can now interpret these disclinations as being fluxes of omega, or equivalently, singular sources of curvature in our lattice. All right, so with this in mind, we can now consider adding disclination to our continuum theory by making use of the fact that lattice disclinations enter as curvature in the continuum manifold. So to do this, we want to now take our Dirac fermions and couple them to our frame field and the spin connection. So if I do this and look in our standard GR textbook, I find this equation for a Dirac equation in curved space, where our covariant derivative now involves both our gauge field A mu as well as our spin connection omega mu, which ended with a term proportional to the C4 angular momentum shown here in brackets. This coupling to curvature in our theory leads to a Win-Z term in our effective response theory shown here, which is the term we saw earlier at the beginning of the talk. In the diagrammatic expansion, this term corresponds to this following one loop diagram between omega and A. Whoops. And now the question is, how do we actually understand this from the perspective of the quadrupole insulator? So the first thing we note is that this coefficient S out front is going to be 0 for a trivial insulator and 2 for our quadrupole insulator. If we then take a functional derivative of this Win-Z term, we find that charge is bound to fluxes of omega. And since the 2 pi over 2 disclination, corresponds to a pi over 2 flux of omega, we find the charge of disclination of the quadrupole insulator will indeed be 1/2, consistent with what we found for the lattice model. Additionally, as just a sanity check, we can see that since S is 0 for a trivial insulator, disclinations of the trivial insulator will not bind any charge as we would expect. This is all good and dandy and agrees very well with what we see in our lattice model. But it turns out we can actually learn a little bit more about our quadrupole insulator by looking at the anomaly structure of this Win-Z term. And it turns out that for a system with boundaries, the Win-Z term is not gauge invariant, which implies a boundary anomaly. For those who aren't familiar with this language, a quantum anomaly is basically what happens when you have a non-conservation of a charge based on some sort of quantum fluctuation. And typically the smoking gun signature of a quantum anomaly is that if you take a gauge field and add it to our system, we're going to find that the divergence of our current is going to be non-zero. There's a similar and well-known story about this, which occurs for Chern-Simons theories with boundaries, in that if we have a Chern-Simons theory, as shown here, and do a gauge transformation where we shift a mu by a function theta, we're going to find that the Chern-Simons Lagrangian will be shifted by this boundary term, which is equal to the flux of the gauge field. This is going to then lead to an anomalous conservation law at the boundary, where the 2 current at the boundary is not conserved. And this is actually very well known as the chiral anomaly, and is canceled by the 1D edge current of a quantum Hall insulator, for example. Now, for the Win-Z term, we can all then look at what happens when we have a gauge transformation where A is again shifted by some function theta. And here we see there's also an additional boundary term at the boundary of our quadrupole insulator. But here, the term is actually going to be proportional to the flux of omega, not the flux of A. This is then going to lead to an anomalous conservation law, where we're going to find that our electromagnetic 2 current at our boundary is not conserved when you have fluxes of omega, or spin connection. This means that we now have a mixed anomaly between U1 charge and C4 rotations at the boundary of our quadrupole insulator. And we can understand this very well by taking this integrated form of the expression, where we find that if we add disclinations to the interior of our quadrupole insulator, we're going to find that the charge at the boundary of our quadrupole insulator will change. And while it might seem like a very kind of abstract field theoretic approach to it, we actually can understand this anomaly between U1 charge and C4 rotations very easily and very geometrically too. So our starting point would be to consider a quadrupole insulator with no disclinations. Because it had no disclinations, any sort of regularized boundary will have an even number of corners, and each corner is going to have a half integer of charge. Because of this, the total charge at the boundary of the quadrupole insulator has to be an integer. And we can see here, if we have no disclinations and 4 boundaries, we then have 4 corners. And so somewhere between +2 and -2 charge at the boundary, so 0 mod 1. Now, let's look what happens when we have a non-vanishing number of pi/2 disclinations in our system. So when our boundary has an even number, when there's an even number of pi/2 disclinations in the bulk of our system, our boundary is going to have an even number of corners. And similarly, when there's an odd number of pi/2 disclinations, our boundary is going to have an odd number of corners. Again, the corners of the quadrupole insulator are going to have a half integer of charge, from which we can tell that the boundary charge is going to be an integer when the disclination number is even, and going to be a half integer when the disclination number is odd. So for example, we can now look at this picture here, which has a -pi/2 or a -1 disclination in the bulk. And you can see to go around this system, we have to have basically 5 times, where we form corners. Each of these corners is then going to have exactly half an integer of charge, leading us to a net half integer of charge at the boundary of our quadrupole insulator. This is exactly what we understand from this equation right here. We can now interpret this delta sign in front of the charge as being the difference in charge at the boundary versus a system that has no disclinations in it. And this actually points to a very general connection between the corner charge and the disclination charge. Say, for example, that I only knew about the corner charge of my system. I had no idea about the disclination charge, and I knew that charge would be conserved. I know that adding a disclination to the bulk of my system will add an additional corner to my boundary. That corner will add an additional half integer of charge, and as such, there has to be an additional extra half integer of charge somewhere in the bulk, such that the entire amount of charge in our system is a full integer, as it must be for any well-regularized system. Because of this, we can also then infer that a disclination of said system with corner charges must necessarily be a half integer. Similarly, if I imagine a system that has gapped boundaries, I don't know anything about corner charges, but I know that disclination by a half integer of charge, I can imagine taking a system with boundary and adding a disclination to the center of it. That disclination is going to bind half an integer of charge and reduce a new corner to my boundary. Since we have to have a full integer of charge, and we already know that disclination has half an integer of charge, there has to be an extra half integer of charge somewhere, which we can then safely assign to being one of the corners, indicating that said system has corner charges. So as we can see, that's a very nice and natural connection between corner charges and disclination charges in these rotation invariant higher order systems. Any questions here before I move on?
Actually, I'm not sure if you're going to talk about this, but it seems that if I write the field theory or look at the field theory, naively, I want to potentially I could try to set n to be whatever I want it to be and the omega to be whatever I want it to be. But I guess here you're kind of saying I cannot actually do that, and there must be some microscopic or I don't know local relation between n and omega. Is that what I should expect?
Yeah, so this is actually a very good question. So there's actually a little bit of a complication here when dealing with these, basically using omega to model disclinations or lattice effects. And this arises from the fact that we look at our Dirac fermion. So let's go back a handful of slides if I can. So our original lattice model has only a C4 rotation symmetry. But if we look at low energies, we have a Dirac cone. A Dirac cone has a full U1 rotation symmetry. And so there's an enlargement of the symmetry at low energies. And so this omega is naively now also corresponds to, going back a little bit, going forward, also now correspond to some sort of enlarged U1 rotation symmetry as well as our C4 symmetry. However, this is only a low energy approximation. So we can assume that at higher energies, we're going to need additional terms. We're going to break down this U1 gauge symmetry down to really the true C4 gauge symmetry of the actual theory. Those terms are going to obviously correspond to higher contributions I'm ignoring for now, but we can safely assume that only terms which are basically require C4 gauge transformations are going to be valid. And so that actually means that our fluxes have to be quantized in fourth powers of unity. We can only have fluxes of 0, pi over 2, pi, or 3 pi over 2. Other fluxes will not be gauge invariant. Does that answer your question?
Actually, yeah, can you, yeah. I'm actually asking if you, just actually the previous slide.
Oh, yes, please.
Yeah, so just this effective Lagrangian, I'm just saying that naively, if I handed this without any context, I would imagine I could make n to be whatever I want it to be, and omega be whatever I want it to be.
Oh,
completely
yeah,
independently. But on a lattice, it doesn't seem like, I mean, it's exactly the kind of thing you talk about. I think the corner charges are calculated through the first term, the disclination charges are calculated through the second term, and overall the whole thing must be charge neutral. So it looks like there's some secret constraint between the first and second term, which is not completely obvious from just the Lagrangian itself. That's what I'm saying.
Yes, yeah. So there is, yeah. So I would say there is some sort of a some sneaky physics in this S term out here. This coefficient S actually plays somewhat a major role when you have a combination of disclinations and domain walls, because you can imagine that if you have a domain wall between a trivial insulator and a topological insulator, S goes between 0 and 2. And you're actually, in this formula right here, this J formula, I've assumed that S is constant. Really, S should be inside the derivative. And so we're actually looking at our fluxes of S times omega. And S actually is going to depend non-trivially on N, which is where that sneaky correspondence between N and omega you were talking about occurs. So this basically, this coefficient S depends on the vector field N in a non-trivial way, which I've glossed over a bit here.
I see. Thank you.
You know, very good question. Thank you. Right. Okay, let's get back to where we were. Yeah, so now going forward, we can now try to, since based on our anomaly argument we already saw, there should be some sort of a connection between our corner charges and disclination charges. And the question then is, how can we put it on more equal footing? And the way we decided to do this by using the observation that if we look locally, you can't differentiate a non-constant vector in flat space from a constant vector on curved space. And because of this, so let's say we look at this vortex configuration shown here, and we compare it now to a constant vector on a cone. Obviously, the left is not a constant configuration, while the right is a constant configuration. And importantly, if we look at what happens just in this red region right here, we can see we actually cannot tell the difference between the two of them. They both look the same, If we want to actually figure out there's something different between the two of them, we have to use a global property such as curvature to identify them. All right, so based on this, how can we kind of formally show there's some sort of equivalent between a non-constant vector and a constant vector plus curvature? So with this in mind, let's consider a non-constant vector n on flat space. Our first step to understand this connection will be to define a local SU2 rotation big omega, which is going to rotate our non-constant vector n into a constant vector big N as shown here. Based on this big omega, we can then write this expression for the change of our vector n, where the new field B we've added is constructed based on the derivative of this big omega transformation. Now, if we pop open our general relativity book again, we're going to find this expression looks like what you have for a parallel transport equation of this vector n with respect to some sort of a new affine connection B. And importantly, the fluctuations of n are now encoded in this new field B we've introduced. All right, we can now look at the same problem now if we include both curvature and from the lattice, and we now find that following our same step before, adding our rotation omega, we find that now the expression for the change in n is given by this. Now we can see that there's both the effective connection B as well as our physical spin connection omega both appear here. Following our same GR textbook intuition from before, we can now identify this expression as being the parallel transport with respect to two geometries. First, there is a physical geometry, which is going to encode disclinations, which is omega. And second, the effective geometry B, which is going to encode domain walls and corners. Now, let's try to use intuition to better understand our fermionic theory. So we can start off with our normal fermionic theory defined in curved space with a non-constant vector n. We can rotate our entire theory by big omega, the same big omega we defined before. This leads us to a new theory, which has a constant vector big N, but we can see now that our covariant derivative now involves both our physical geometry omega. We've also now found a new term B arising from the effective geometry as well. So we now have that instead of having a Dirac fermions coupled to some sort of a non-constant vector n, we now find that instead we have traded in that theory for a new theory of fermions coupled to a constant vector or some sort of constant mass term, but now have introduced a second source of geometry on top of our original geometry. We could then follow the step from before and integrate out our fermions to find our effective response theory. And we now arrive at the equation from before, which includes our mutual Chern-Simons term B, as well as our spin connection omega. And while the geometric term, this omega dA term, aka the Win Z term, is greatly the same as what we saw before, we're going to need a little bit of a dictionary to go between our previous knowledge and what we saw here. And if we pull the lever a little bit, we're going to find that half fermions of n are going to correspond to pi vortices of B. And similarly, corners of the quadrupole insulator are going to bind pi vortices of B as well, which we can tell by the transformation laws of B. This is very good, and from this and what I've said earlier, we can now tell that this effective field theory is going to describe all the long-distance physics of the quadrupole insulator without resorting to any sort of a real lattice regularization. Yeah, so I guess before I move on, any questions about this? All right, yeah, so I think having now discussed the effective field theory, we can now try to push it forward one more, and we try to generalize this effective field theory for the quadrupole insulator to some sort of a fractional response, the same way you can generalize a Chern-Simons theory to some sort of a fractional response that would describe a fractional quantum Hall insulator. So with this in mind, we can define the fractional version of the quadrupole response as follows, which differs by a factor of 1 over m out front. It should be noted that this 1 over m factor actually makes this theory non-gauge invariant on periodic manifolds. And so really we should be expressing this whole theory in terms of some auxiliary gauge fields. But for brevity, I'm just going to leave it in this form. But again, if you really want to understand this theory, you have to really use auxiliary gauge fields the same way you do for the fractional quantum Hall effect. So this response theory is going to describe a fractional quadrupole insulator with C4 symmetry enriched topological order, or basically meaning that the anyons of our topological order are going to have non-trivial C4 angular momentum. The topological order for this theory is going to be of a doubled 1 over m type, which corresponds to roughly a Laughlin 1 over m state along with a second minus 1 over m state, leading to a non-chiral boundary. And here, the anyons are going to have charge 1 over m owing to the two Laughlin states. Now, if we look at the corner and disclinations of the system following our same steps as before, we're going to find the corners of the system are going to bind charge 1 over 2m, and the disclinations are also going to bind charge 1 over 2m. And for the same reasons we saw earlier, these anomalies guarantee that these disclinations and corner charges have to be the same. Importantly, for this theory, the charge is going to be defined modulo 1 over m, which is the lowest anion charge. However, since these disclination or corner charges are 1 over 2m, we actually cannot screen the corner charge or disclination charges. In other words, these charges are even further fractionalized beyond the already present fractionalization of our anion charges. This can be generalized then to other sorts of abelian topological order by, say, some well-known methods such as the K-matrix approach, and gives a new route to understanding what I'm going to call higher order topological order, which are going to be topological ordered systems that instead of having gapless boundary modes, have some sort of corner degrees of freedom instead. All right, so that gets me to the end of my talk. So in conclusion, we find that two-dimensional HOTI'S are described by a theory with a physical geometry, which encodes lattice defects, as well as an effective geometry, which encodes domain corners. This theory correctly describes the charge profile of the quadrupole insulator in the presence of lattice defects and domain corners. And we can also generalize this to a response theory for insulators with higher order topological order. And to conclude, some open questions. First, can we use similar method to understand higher order topological insulator with other crystalline symmetries, such as a mirror symmetry, or perhaps magnetic crystalline symmetries, which are, I think, very interesting to me personally. Additionally, can we use these crystalline responses to identify higher order topology in real materials? As I noted before, most HOTI'S and experiments are primarily metamaterials. And I think one reason for that is kind of hard to actually construct a real corner in an actual material sample. There are some etching techniques, but in general, it's pretty hard. And so these crystalline responses might be a more interesting way of diagnosing the bulk physics. They are entirely a bulk and don't require any sort of domain wall to be present. Finally, we can ask what sort of models or materials might be able to realize this sort of fractional quadrupole insulator, or more generally, other higher order topological orders. With that, I'll end my talk. Thank you very much again for having me. And I will now open it up to questions.
Any questions? Actually, I do have one, even though I've asked plenty. So the response theory, the effective Lagrangian that you wrote, if I don't care where n come from, really look a lot like a fractional what do you call that? Quantum Hall paramagnet.
Yes, no, it's the same field theory.
Yeah, it's exactly the same. So other than formal resemblance, is there some deeper connection between the two, or is it just so happen that they're looking like the same thing?
I would say that they're, I'm see if I can get back to that equation you're talking about. There we go. That's a good question. I'm a little bit more on the side. I think it might be kind of just a coincidence. You can only write down so many topological field theories in 2 dimensions. Here, I think my main intuition here is trying to understand this as being your domain wall configuration should be some sort of a bosonic, some sort of a classical theory, which is some sort of a bosonic theory or some sort of a sigma model like this. I think the intuition behind the quantum Hall ferromagnetism was quite a bit different from that. So I don't want to, I think, overpush an analogy. Okay. But yeah, so it is the exact same field theory. This also actually, interestingly enough, describes quantum spin Hall insulators as well.
Right.
Yeah. So again, there's all physics is connected, but I would be I'm a little agnostic here. I'm going to say that it might just be a coincidence. There's only so many field theories you can write down.
Fair enough. Yeah. Any questions? Is anything on the okay? I don't think there's anything on the chat. So I guess thank Julian again.
Thank you very much.
You, and I'll see you on Monday.
See you then. Looking forward to it.
Okay, that's it. There's snacks in the back, so. Okay, we're gonna end the meeting now.